Welcome, everyone. Consider this explainer your essential review guide, setting the stage for what I like to call our syllabus of reality. We are embarking on the very first chapter of advanced undergraduate physics, a true masterclass on the rigorous foundations of motion. So whether you're brushing up on your memory or locking down these concepts for the very first time, we're going to build a rock-solid mathematical understanding of exactly how the physical world operates. Okay, let's dive right into this. Here's our agenda for today. We're moving from the foundations of physical measurement, straight through vectors and dimensional analysis, into the geometry of motion, dynamics, and force, and finally, we'll wrap up with some essential practice problems to get you exam ready. All right, Section 1, Foundations of Physical Measurement. To really get what we're doing here, we got to look at the historical origins of our terminology. The word physics itself actually comes from the Greek word physis, which literally just means nature. And that's our foundational goal, right? We're looking for those universal laws that apply to the whole shebang, from a falling apple to a massive planetary orbit. We achieve this through careful observation, experimentation, and some pretty heavy-duty mathematical reasoning. So how do we actually uncover those laws? We use the iterative scientific method. Think of it as a continuous six-step loop: observation, hypothesis, prediction, experiment, analysis, and refinement. Now, here's a highly practical tip for your university lab work. When you're designing a controlled experiment to rigorously test a brand new hypothesis, your absolute main goal is isolating variables. Let's say you want to see if mass changes how fast a pendulum swings. You have to keep the string length and the release angle exactly the same. You only change the mass. If you change a bunch of things at once, well, your analysis is going to be completely muddled, and your refinement step will basically be a shot in the dark. A solid physical theory has to be falsifiable and predictive. And to measure all those variables, we need units. We build everything on fundamental blocks: masses in kilograms, length in meters, and time in seconds. But, and this is crucial at the advanced undergraduate level, you have to be super comfortable with how these base units mathematically combine to create derived physical measurements. Take force, for example. It's not just a Newton. Under the hood, it's actually a kilogram meter per second squared. Energy is a joule, right? But that expands out to a kilogram meter squared per second squared. Knowing these underlying structures is absolutely non-negotiable. Moving right along, Section 2, Vectors and Dimensional Analysis. Before we even think about plugging numbers into a calculator, we use the principle of dimensional homogeneity. It's really just a formal way of saying that in any valid physics equation, both sides have to match perfectly in their fundamental dimensions. Look at the classic kinematic equation. Final velocity squared equals initial velocity squared plus 2 times acceleration times distance. If you break all that down, both the left and the right sides boil down to dimensions of length squared over time squared. Seriously, dimensional analysis is going to be your absolute best friend for checking equation consistency during a stressful exam. If those dimensions don't match, you've definitely made an algebra mistake somewhere. Next up, we really have to strictly separate our quantities into scalars and vectors. Scalars are all about magnitude, just the amount. Think mass, time, temperature. But vectors have magnitude and direction. Let's use a simple real-world motion scenario. Driving your car at 30 miles per hour, that's a scalar speed. It tells us how fast you're going, but not where you're headed. But driving 30 miles per hour directly north, boom, that is a vector velocity. In physics, those are two totally different pieces of information, and treating a vector like a scalar will for sure lead to fundamentally wrong answers. Let's walk through the mathematical rigor we expect at the university level for basic vector operations, specifically component addition. Think about this step-by-step process. Say we have vector A as 3i plus 4j and vector B as negative 2i plus 5j. To add them together, we just independently sum up the x components. So 3 minus 2 gives us 1i. Then we sum the y components, 4 plus 5, giving us 9j. The result is a brand new vector, I plus 9j. It's that clean. And this algebraic method perfectly mirrors the physical geometric rules of placing those vector arrows head to tail. Okay, Section 3, the geometry of motion. And this brilliantly illustrates the story of motion. Picture tracking a continuous trajectory mapped out across a two-dimensional coordinate system. Imagine our point P is just moving through space. At any given time t, we can pin down its exact position, with an x-coordinate and a y-coordinate. By tracking how those coordinates change using vector calculus, we can precisely map out its velocity and acceleration curves. The real secret to unlocking two-dimensional paths is Galileo's principle of independence. He figured out that horizontal and vertical motions proceed completely independently of each other. Think of a simple everyday example, like a baseball thrown from the outfield. The horizontal motion is uniform, it's just coasting at a constant velocity, while simultaneously that vertical motion is undergoing constant downward acceleration because of gravity. Those two independent axes seamlessly combine together to create that beautiful parabolic curved trajectory you see on the field. Let's shift gears to Section 4, Dynamics and Force. To really talk about inertia, we have to cite the master. In his historic Principia, Isaac Newton wrote, "Every body perseveres in its state of rest, or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon." To put it simply, objects are lazy. A soccer ball sitting on the grass is going to stay perfectly still, and a hockey puck gliding on basically frictionless ice will just keep gliding forever, unless an external force, like a swift kick or a hockey stick, compels it to completely change its velocity. Now let's contrast two totally different types of acceleration. First, consider uniform circular motion. Think of an everyday spinning object, like a vintage vinyl record or a tetherball. Even if its speed is perfectly constant, its direction is constantly changing. That means the velocity vector is changing, which requires a centripetal force constantly pulling it towards the center. Now contrast that with purely linear acceleration. Think of a highly controlled air track experiment where a constant force causes a mass to just speed up in a perfectly straight line. Two totally different geometric manifestations of F equals ma. So the crucial point here is that tackling dynamics at this level requires a really systematic method. You literally cannot just guess formulas and hope for the best. You need this 7-step process. Read and understand the problem. Identify the variables. Draw a precise free body diagram. Choose your coordinate axes wisely. Apply Newton's laws by breaking forces into components. Check your answer to see if it actually makes physical sense, and then clearly state your result. This framework is your absolute lifeline for managing complex exam scenarios without panicking. Finally, let's wrap things up with Section 5, Essential Practice Problems. As you prep for your upcoming evaluations, mastering specific formal derivations is going to be absolutely critical. You need to be able to seamlessly run dimensional analysis on equations like v equals the square root of 2gh. You've got to be completely flawless in your vector operations. You should know how to formally derive the maximum projectile range equation completely from scratch. And you must be prepared to apply uniform circular motion to advanced historical applications, like finding the cyclotron frequency of charged particles zipping through a magnetic field. Before we go, I want to leave you with a rather provocative thought to chew on. We've just seen how brilliantly classical mechanics describes our macroscopic world, from thrown baseballs to spinning records. But if these laws are so incredibly perfect, what actually happens when we scale way down to the subatomic level, or scale way up to the mass of a black hole? How do these elegant Newtonian laws break down, or transform, in modern physics' search for quantum gravity and a unified theory of everything? Keep that intense curiosity alive, you guys, because our exploration of physical reality is really just beginning.